All right, so today we're talking about big picture day for chapter 3. And the whole thing about chapter 3 is the derivative. Okay? And specifically, what does the derivative do? Okay? And the idea is the derivative is the instantaneous rate of change. The idea being, how fast is it changing right now? How fast are you going right now? How fast is your speed changing right now? That's the idea. Okay. So in physics, we talk about, hey, the rate of change of displacement, we call that velocity, right? The rate of change of velocity is called acceleration. If you can think about that for a minute, okay, if x is how fast I'm trying, x is displacement, and let's say you're falling out of an airplane or jumping off a table or a roof or whatever, I don't care. Plus 6 or whatever. If I take the derivative of that, I'm just going to tell you right now, the derivative of that happens to be, we write x prime as the derivative, happens to be negative 9.8t plus v sub o. And then the second derivative of that is the rate of change of this, which happens to be negative 9.8. Now someone might say, Groom, wait a minute. Are you saying, Groom, Mr. Groom, are you, what? This is linear, and you're saying the rate of change of linear is the slope of it. Literally, that's what I'm saying. Well, now if everything was linear, that'd make my life easier. You are not wrong. Furthermore, let me ask you this question, sir. If your speed was, I don't know, 6 miles per minute, 6 meters a second, then x prime, the rate of change, of course, of that would be 6. How fast is that changing? Well, sir, what part of a constant do you not grasp? It isn't changing, dog. It ain't moving. Okay? And so what we're going to be doing is looking at, obviously, some polynomials, but we're looking at a variety of different ones. What about a sine function, Groom? I bet we're going to need a function that varies similarly to the sine function to describe what its slope is. Because right here it's positive slope, and then it's zero slope, and then it's negative slope, and then it's negative slope still, and then it's zero slope, and then it's positive slope. Shut up. Groom, are you saying that it was positive, positive, positive until it got to zero? That's right. And what was here? Zero. Wait a minute. And then it was negative slopes until I got to here, yes? That's right. Shut up. Are you saying that if x is sine t or something, maybe I write y equals sine x. I should write that way because then people won't freak out. Mr. Groom, I'm confused. That'd be cosine? It sure is. It sure is. It sure is, dog. So we'll be running through some. Obviously, some you're going to memorize. Some you're going to have to work through. It's going to be kind of ugly and gross, and that's how life goes. But what's going to happen is this is like, dude, how... Oopsie daisy, I came unplugged. How fast is it changing right here? Well, it's different here when it's barely starting to go down than it is here when it's starting to come down. It's still going down, but it's starting to taper off again. That's where it's going the fastest rate of change, yes? True that, homie. And is it fast as negative rate of change? Yes, because it's going down to be a maximum, yes? Oh, rate of change anyway. And so we'll be looking at that. And we'll be kind of talking about, well, what about what's going on with our graphs here? In fact, we can be doing this kind of thing. Nice. Mr. Groom, what's the slope right here of the tangent? In other words, if I drew this line across here, that'd be a tangent line, yes? And the slope of the tangent line is the same as what's going on there. Well, the slope there is 0, obviously. What kind of slopes did you have over here, sir? Well, not very big, positive slopes. Okay, I got you. And what do you have here? Well, they're negatives. Bloop, bloop. And then what do you have here? Oh, 0 again. You with me? Bloop. And what do you have here? Well, that's 0 again, right there. But whoa, holy cow, that's a steep slope, bud. Whoa. And then what do you got? Well, these are all negative slopes. Chong. Something like that. If this is f, we say this is f prime. Wait, what would f double prime be? Well, it would be the prime of this fella. Hey, what's the slope here? 0. Hey, what's the slope here? 0. Shut up. No, I will not shut up, sir. Let's do this thing. So if that's the case, then what happens here? Well, that's 0 slope. What kind of slopes you have? Well, you had negative slopes. You had negative slopes. And then what? And these are all negative slopes. In fact, I would argue that, oh, poop. I would argue that this is the steepest negative slope is right there, yes? So it's going to be kind of like this, and then back up to 0, yes? Because, it's got to get back to 0. And then it's got to get back over here, but this is about the steepest. It's going to be right in this neighborhood somewhere, and then down like that. F double prime. Groom, can we do another one? Bro, theoretically, we could go forever, right? Theoretically, we could go forever. And we will. It'll be great. Notice that wherever f prime has a 0, like right there and right there and right there, you're either going to have a maximum or a minimum or a maximum. Usually, there's a couple other situations where that's a little bit different. It's kind of a lie, but pretty close to being true. And so, of course, if we're going to find max and mins, well, first derivative set equal to 0. That makes sense, right? Now, this guy here actually turns out it has a 0 slope right there. It turns out it's a 0 slope. It's flat and then goes back up again, technically speaking. And positive slopes, they're getting smaller as I get closer, and they get smaller and smaller and smaller. They're actually 0 briefly, and then they go back up again. Whoa, that almost looks like x squared. It does almost look like x squared, doesn't it? Interesting. So we're going to spend a lot of time discussing that. What does that mean? What can we do with it? Now, another thing we will do with them is Notice that from here to here, it is concave. That is, it opens concave down. And then from here to here, it's concave up. So we'll spend some time talking about that as well. In terms of how does that mean it's a maximum or a min. By the way, without the graph, of course. A lot of times you won't be able to see the graphs. Things like that. So we're talking about that. Identifying is this a maximum or minimum location, even without a graph. And doing things along those lines. It's really quite straightforward. Pretty easy to do, in fact. Okay. Now, what would happen if your function was discontinuous somewhere? It's an excellent question. Thank you for asking it, Parker. That does not touch the x-axis, in case you're wondering. It's pretty close. This is our guy 1 over x, right? What is his slope? These slopes over here are negative slopes, yes? So they start off pretty small negative, and then they go really big negative. Whoa, they kind of look like that. And here they are big negative slopes, and they kind of come up and they kind of just peter. Dude, that's kind of neato. It is kind of neato. But what happens at 0? What is the slope at 0? Well, it was down here at negative infinity, just about, right? All of a sudden, bam! Instantaneously, it's up there. That's going to be a problem. Are you with me? That's going to be a problem. We talked about our buddy squirt x, square root of x. Hey, what was he doing before 0? Well, he didn't exist. And then he existed, but there was none of them. Again, having no pizza and then pizza not even being a thing are two wildly different things, yes? All of a sudden, bam, we've got pizza. How fast that happened? Right now. Well, that's going to be a problem. What if you have a step function? Whoop, bam! How fast did it go from here to here? Well, it went instantaneously. Remember, slope, back in Algebra 1 is, it's rise over run. But if your run is 0, we've got a problem, yes? Because that means that we've got infinita for a slope, yes? That's no bueno, senor. Es no bueno. No bueno. And so we'll be looking at that quite a bit. Now, the premise of the whole thing, obviously we're going to use a lot of these things. We're going to find them. We're going to spend some time. How do you take the derivative of this one? How do you take the derivative of that one? But Groom, how do you take the derivative of that one? Okay, I know. But what we're going to do is actually this. Suppose you got your guy f of x. And suppose you're here at x. And you want to know, what is this slope of this tangent line? Well, you need 2 points on the line, right? Cool, but you can't have 2 points. So what I'm going to do is I'm going to come over some h units. Are you with me? And that's x plus h. And so up here you've got the point that's actually on the line, f of x. And you get another point that's pretty close to being on the line. Now, notice that if I include both of them, we have what's called a secant line. Secant line, because it passes through twice. And this point is f of x plus h, comma, what are you doing, dumbass? It's x plus h, there you go, comma, f of x plus h. Atta baby. Nice. And so if you find the slope, well then by definition, the slope is, well, it's f of x plus h minus f of x over x plus h minus x, which is just h. Did you see that? But Groom, what if I take the limit as h goes to 0? Well, that's interesting. Now, obviously, that's going to be a problem. True dat? It's going to be a problem if h is 0 because why? Because obviously it's on the bottom. But what if I told you that this is the very definition of a limit? It's not what is it at 0, it's what is the limit as we approach 0. And so we're going to see quite a few of these. It's going to be kind of fun. We're going to run through a ton of them. The limit definition is really quite straightforward. So here it is. I'm going to do a couple of examples today, and then we will pick it up on Tuesday. Yeah, Tuesday. Tuesday, is that right? Wait, is that right? I gotta check my schedule. Just a moment, please. 1 moment, please. Hold, please. Oh, that's right. So, yeah, on Tuesday, I'll also be talking to you a little bit. Yeah. All right. Oh, yeah, tomorrow I'm talking to you in class. Duh. So f of x equals x squared, let's say. Cool. What would f of x plus h be? Well, it'd be x plus h squared, obviously. So f prime of x, by definition, is the limit as h approaches 0 of x plus h squared minus x squared over h. Now, I need to simplify this, and that needs to go away. You with me? That has to go away. And so it's the limit as h goes to 0 of, now this is, if you FOIL it out, x squared plus 2xh plus h squared minus x squared over h. What I just did right there, you're going to have to do on every single problem something akin to that. And if you've done it right, watch this. What you just saw there, okay, remember, that is the rise over the run, right? This is what we're doing. So the rise is on top. Rise is a change in y, delta y. It's a change in y. What we're saying is the ching, the parts that just have x in them, just x, no h at all, that's what they had in common. And what's left over is the change in y. That will always be true. And again, if you've done this correctly, friend, what will you have always on top? Everything on top will just have an h in it. Are you with me? Which is cute because what happens? Ching. And so you have 2x plus h. And what is the limit as h goes to 0 of 2x plus h? Well, this piece goes to 0. The limit is 2x. And you're like, Groom, that's it? Yes. F prime of x is a function. Are you with me? It's a function. And so if I tell you, hey, what is the slope at 3? You literally just plug it in, you get 6. That's it. That's the slope at 3. That's what we're going to be doing. Okay? It's going to be a good time. Suppose your function was this fella. Yeah, I want to do that one. Sine x. Groom, I thought you said it was already. We already know what it is. Well, I know what it is, and I kind of hinted at you what it is. And I think we can probably convince ourselves what it is. But let's do the actual math, shall we? I'm always down for a little bit of extra math. That's a good time. So it's going to be the limit as h goes to 0 of sine of x plus h. Oop, what are you doing, stupid? You don't need 2 divide bars over h. Now, that right there, my man, is a sum for the sine function, a sum of angles. Wait a minute. There's an identity for that. I know what it is, Groom. Sine's the same sandwich. So it's the sine of x, sine of h, minus sine of x, no, plus the sine of x, sine of h, sine of x, doesn't matter which way you do it. Oh, no, it isn't, you dumbass. Sine cosine, sorry, cosine. And then sine h cosine x. There we go. Dang, kind of stupid, Mr. Groom. Yes. Right. Minus sine x over h. I had to think about that for a minute. Now, I'm going to rearrange a few things here so don't get all weird. What are you doing, Mr. Groom? Well, what I'm doing, sir, madam, is I am tweaking it to make it to where it's a little nicer for what I want to do. I'm going to write this the sine of x, cosine of h, plus, minus the sine of x over h plus the sine h cosine x. Now watch this. What happens to this guy? As this thing goes to 0, what happens? Oops. As that goes to 0, this goes to 1. You with me? And what is, then it's going to be sine minus sine, which is 0. 0 over, so anyway, the point of the matter is this piece goes to 0. This, what is the sine of h over h? Well, that's 1. So you get cosine x. Yay. We'll do others. Groom, please do a cubic for me. Yes. Okay, weirdo. So f of x is a cubic. Great. Which is x cubed plus 3x squared h plus 3x h squared plus h cubed. Okay, and so the limit as h goes to 0, which of course is f prime, is x cubed plus 3x squared h plus 3x h squared plus h cubed. Again, if you have any just pure x's left on top, you screwed up. Okay, so and if you let h go to 0, these pieces both go to 0, yes? And you're left with 3x squared. That is your f prime. After a while, we're going to learn some shortcuts. There's a few special ones. And then after a while, you're like, Groom, what if it's some god-awful nasty thing? What if I have to take the derivative of, oh, I don't know, x sine x or something? Oh, that's awful. Yeah, it's not as bad as you think, but it's not great. Okay? Or what if I take the derivative of, oh, I don't know, sine of 3x squared or some bullcrap? I don't know. Oh, no. Listen, we have rules for all of those, okay? So the first part of this chapter, you're going to find we're doing a lot of application, starting out a little bit of application of it. And then the very basics how we do derivatives. As we move on, chapter 3, and then into chapter 4, we're going to be doing a lot of different tools. Like, hey, what happens if you have this thing, which is a function in a function? What if it's a product? Okay, what if it's a quotient? Good, all those are great questions. Thank you for asking them. We'll get to them in due time, sir. Due time. But anyway, it's just different ways of taking the derivatives. Oh, that's cool. And then chapter 4 is going to be primarily about applying the derivatives to do cool things. Okay, that's basically the idea. Okay? And so that's kind of where we're going in this chapter. That's the kind of the big picture of where we're going. That's chapters 3 and 4, basically, kind of the big picture of those two chapters. Just chapter 3 right now. We're going to have fun. Okay? Oopsie. And so tomorrow we will be discussing the formal definition a little bit more and start going on from there. It's actually quite enjoyable, quite fun. Okay?